Okay, so we've talked about how the radical symbol can be understood in the context of complex numbers or imaginary numbers and solving equations that have a complex solutions or have imaginary components in the equation or the solution, and just how the radical mixes in with complex numbers. But what I wanted to do in this video was also think about the idea of, if we're given an equation like x cubed minus 1 is equal to 0, and we want to solve this equation, but a lot of times you might be given a statement like, only consider the real solutions. And so really what that's more saying is, in the entire context of the problem, even in the equation itself and in the solutions, we're only in the all real numbers domain. So we're not even considering imaginary numbers in any sense, right? You're just considering all real numbers. Okay, so let's think about how the radical gets used in a situation like this. Okay, so once again, let's lay out exactly what the radical symbol means. So first of all, the radical symbol means it's the principal nth root. Some people think that a radical symbol is you only use the term principal root if it's a square root or if it's an even root. No, that's not true at all. The radical symbol in general is a principal nth root, okay? And what it means is that, so you have this radical symbol here. This is the argument of the radicand. This is the index, okay? What this means is that there's going to be, this is the principal root is, it's kind of like it's saying that it's a function. When you have a principal root symbol, a radical symbol, there's only going to be one answer to this. Even though there might be multiple roots of A, there might be multiple nth roots of A, there might be multiple numbers that when you take them to the n power, you get A. The principal root is saying that it's specifying just one of those roots. So this is going to be one number B, to where this means that B to the n power is equal to A. Okay. Now, another thing to note, though, is that when we're defining the principal root like this radical symbol, we're thinking in the real numbers domain, where this is like what we defined this in pre-algebra, where we're only thinking about the possibility of real numbers. So right now, A could be any real number, B can be any real number, and n is greater than 1 and is an integer. Okay, so like, we don't do zeroth roots or negative. The end is never like 1, 0, -1. It's 2, 3, 4, 5, etc. Okay, so just keep that in mind. Right now, we're thinking about A is a real number, B is a real number, n is greater than 1, and n is an integer. Now, so if we're just thinking about in terms of real numbers, the real number domain, then if n is odd, if it's an odd index, then we're done here. There's no issues in the sense that we don't have to say, well, no, but A can't be less than 0. That's going to create a problem. Or we have to restrict B because B could have two possible or more than one possible answers, so we have to apply restriction. No. When it comes to odd roots, we're done across the board. A can be any real number, positive or negative, and we're going to have one root, one B value, to where when you take B to that odd integer power, you're going to get A. Okay, so great. But what about if n is even? Well, in that case, we're going to have to apply some restrictions. So we have to say that, so if n is even, then there's two things we have to specify here. We have to say that A has to be greater than or equal to 0. Okay, it can be equal to 0, but that's not enough. We also have to say that B has to be greater than or equal to 0. Because, okay, we specified that you can't have a negative number as the radicand. That's fine. All right, so let's say you have a positive number like 4 with an even root. Well, there's a problem there because there's two numbers that when you take them to the, let's say n was 2, take them to the second power, you get positive 4. So to make this a function, we have to specify we're going to return the positive root. Okay, and that's it. That's it. That is the radical. And again, this is the principal nth root of a. For across the board, no matter what the index is, no matter what the radicand is, this is the principal nth root of a. It was defined in the context of real numbers. And so this is mainly what you're going to, when you see a radical, this is mainly what you're going to be thinking about. This definition here. Radicals are really are associated with real numbers. Okay, so now this is confusing though, because that we did mix in a little bit of imaginary numbers with the radical. There's a definition that says that, okay, if you have a case where we expand this to where we can evaluate with a radical, we can have an index of 2. An index of 2, so when there's no index given that implies 2, with a negative number underneath. And from the original definition, this was, there would be, we would say there's no solution. From the original definition, if we had an even index with a less than 0, we'd say there's no solution. But we expanded that a little bit to where we can actually write this like that. Okay? And so that brings imaginary components in, or complex numbers into it. But that's as far as we went though. Like, so you can't do this with an even root other than 2. You can't. This is not equal to. You can't do that, right? Because 4i to the 4th is not equal to negative 16. So this only applies to the square root. All right, and then but outside of this property here, this is as far as we went when it came to radicals and complex numbers, or numbers with imaginary components in them. That's it. Okay. Now, so we mentioned though that you do have radicals in the sense that if we were solving this for all possible solutions, so we added 1 to both sides, okay, and we would take the cube root of both sides. Well, okay, yeah, we have a principal cube root here of 1, but in this sense, we're actually asking the question, what are all numbers when you cube them that you get 1? All numbers. And so we're not really looking at this as an actual principal cube root in the same way that if we were solving for, if we had sine theta is equal to root 2 over 2, and we were solving for theta, we introduced the inverse sine to both sides. However, we know that we don't really look at this as an actual inverse sine function, and it's only going to have one output. We ask the question, what are all numbers when you take their sine, do you get root 2 over 2? And we list those out. Since we introduced this to the equation, it's the same idea here. Since we introduced the cube root, the principal cube root symbol to the equation, then we're not really treating it that way. Where in actuality, we're asking the more general question. Okay, so now, and yeah, so but I mentioned though, from there you don't want to go any further mixing, at least for the moment, until you get into complex analysis course. You don't want to go any further mixing in radicals with complex numbers. You don't want to be saying something like this. What is the principal 4th root of 3 minus 2i? Even though 3 minus 2i does have a principal 4th root, it corresponds to the k is equal to 0. We don't want to be mixing those in. We'll talk about all that later. We don't want to be mixing complex numbers with radical symbols. Okay, and I mentioned exactly why we don't want to be doing this in the previous video. Okay, so now, let's think about if we're trying to solve this equation and we're not allowing for any imaginary solutions. And so in that case, you wouldn't even allow, it wouldn't make sense to even have something like x cubed minus I is equal to 0 and solve this. Well, how could you not allow for imaginary solutions if you have an imaginary component in the equation itself? So obviously the equation itself isn't going to have any imaginary components either. So how would we use the radical in that sense? Well, okay, what's going to happen here is that if you think about how this is going to work out, if you add a radical symbol with an odd index to both sides of the equation, then there's no ambiguity. You don't, like in this case here, you don't have to, you can actually just take the exact principal cube root of 1 here, because there's only one answer anyway. It was already a function, the principal cube root was already a pure function to begin with, so there's no issues. Whereas if there were imaginary, if you allow for imaginary solutions, well, we know that any number with any, taken to any nth root is going to have like n roots. Well, in this case, if you're considering only real numbers, there's only one number. When you cube it, you're going to get 1. And if you had x cubed is equal to -8, same thing. There's only going to be one number. When you take it to the third power, you're going to get -8. So with odd roots, when it comes to like applying a principal nth root symbol, radical symbol, to both sides of an equation, if it's an odd index, you just evaluate whatever the exact principal nth root is, and you're done. You don't have to think about the big picture behind it. Okay. Now, when it comes to even roots, let's first think about a square root. Okay, so if we had x squared minus 4 is equal to 0. Okay, well, we know that there's something called the square root property. And this is just for square roots, where if you want to take a square root of both sides, you do this, okay, and you put a plus or minus in front of the radical. So you still have the principal fourth root, or the principal square root of 4 here, but it has a plus or minus in front, and so you're left with this. And it's just this trick, all this trick does is it accounts for all of the possibilities associated with what numbers, when you square them, do you get 4. All you got to do is put a plus or minus out front. Okay, so we already knew how to solve taking an equation where you have to take the square root of both sides. You use the square root property. Now, if we had x squared is equal to -16, what you could actually still use the square root property here, even though this has imaginary components. That's what's kind of nice about I think that's why they went ahead and made that definition with the imaginary component in the radical for the square root, because it works out perfectly. You get, and that's actually correct. If you took 4i squared, you're going to get -16. If you took -4i squared, you're going to get -16. Okay, but you obviously can't do this with like a x to the fourth is equal to -16, because the main reason is because you can't do this. It doesn't have this property. Okay, with the radical symbol for the fourth root. Okay, but even so, though, if we're only allowing for real solutions, then really at this step here, you come to this definition and you see that, well, wait a minute, a is less than 0, so there's actually no solution here. There's no number when you square it that you're going to get -16, no real number. So there's actually no solution. Okay, now, but what about if you have x to the fourth is equal to 16? So it's a positive over here. Well, this is kind of confusing, because there is no property that that says that we can do this. Put a plus or minus like that in front of this root. There's no property for that. But the reason why they don't state an official property is because, and they do for the square root property, is because the square root, if you have x squared is equal to 16, you can call that a property, because that's going to work in relation to all numbers. You can apply the square root property with complex numbers, with just real numbers. It works across the board. Okay. However, when it comes to even roots, other than 2, that putting that plus or minus isn't going to work across the board for all numbers, because we just saw if you have a -16 under here, it doesn't really work that way. You can't. It's not going to work that way. Just putting a plus or minus out front, and it's not going to be that simple. Okay. However, what you can think about, though, is that if you're only allowing for real solutions, then you can actually do this. There's no official property that's set in algebra that tells you this, but if you think about it, you could do this. If you're only considering real number solutions, then this is going to work because you have x is equal to, and then it would be plus or minus 2. Well, that's correct, right? 2 to the 4th is equal to 16, minus 2 to the 4th is equal to 16. Those are the only two numbers when it comes to real numbers that when you take them to the 4th power, you're going to get 16. Like that property that applies to any even power. If you're just looking at the real numbers, then and you're thinking about powers in roots, okay? That idea of it, like for the square root, there's two numbers when you like every positive number, every number greater than 0 has two roots, one positive and the other one the equivalent negative. That applies to any even power. It's not just square roots, right? There's two numbers when you square them, you get 16. Positive 4, negative 4. That's going to be the same thing for any even root. There's going to be two numbers when you take them to that power, you're going to get that positive number. And so in that sense, you can put the plus, or you can use this plus or minus property with the radical. Put that nth radical and put the plus or minus, and that's going to work. They just don't state this as an official property like they do the square root property because it's not going to work across the board. You can't say, you're not going to be able to say if you have x to the 4th is equal to minus 16, you can't, what are you going to do with this? We haven't talked about any property where that involves radicals where you can simplify a negative number under an even index other than 2. And so how do you approach this? Well, okay, if you're thinking about only real numbers, the solutions are only real numbers, then it's the exact same as x squared is equal to minus 4. There's no solution here. You say no solution because there's no number that when you take it to the 4th power, you're going to get, or no real number, when you take it to the 4th power, you're going to get minus 16. However, if you're allowing for imaginary solutions, then it's the same thing as if you had x cubed is equal to 8. You do the cube root of both sides, but then you can do that here, the 4th root. But in that case, you're not really looking at this as a principal 4th root symbol, right? And same here, you're not looking at this as a principal cube root symbol. You're more of asking the question: what are all of the numbers when you cube them that you get 8? There's going to be 3. What are all the numbers when you take them to the 4th power? Do you get minus 16? There's going to be 4. You see, and so that's why there's no, again, that's why there's no property here that they associate directly with radicals like they do with the square root. Because with the square root, it works out great because it's like completely defined across real and imaginary and complex numbers. It's defined across the board. The square root works out. It obviously works out good in this original definition. But then you've got a nice property with square roots that extends them to negative numbers underneath to where you can just take out an I and leave the positive root. Great. It works out perfectly with the square. You can extend the square root property where you take the square root of both sides and put the plus or minus. It extends perfectly if you have imaginary numbers because you can still, if this was a minus 16, then x would be plus or minus 4i. And these are the two roots, the two square roots of minus 16 across the board are going to be plus 4i and minus 4i. So 0 plus 4i and 0 minus 4i. So the square root, the principal square root works out great across all real and imaginary and complex numbers. But we haven't talked about yet how we're going to deal with radicals with even numbers in with even indexes even for complex numbers. We haven't gotten there yet, and we'll talk about that more in the complex analysis course. Okay, so yes, that's the idea. If you're solving equations with radicals where you're applying radicals and there's only real number solutions allowed.